right, hello everyone. Welcome to the second part of this video on this problem where we're trying to find the absolute maximum and minimum of the function f of xy equals xy along the circle x squared plus y squared equals 10. So just a quick recap of what we did last time. We're using Lagrange multipliers to solve this problem, and as in blue are the requirements for Lagrange multipliers. So you're looking for a solution to the system of equations. You see in blue, and we first of all started by taking the gradient of f, and we found what g was, which was basically the other side of the constant and the constraint. We found g, found the gradient of that, and by what we have in blue, we consider the system of equations right here that you see where I labeled them as 1, 2, and 3 in green. And what we did was we went ahead and tried to solve the system. And as I said last time, solving these systems is not easy. It can be quite difficult because a lot of the time you don't know what steps you can use. We forget. But what we tried here was using substitution. So I started by substituting x equals lambda 2y into the x in the first equation. And we got what you see as I'm scrolling down, and we got y equals 0, and we got lambda is equal to plus or minus 1/2. And we looked at both those conditions. For when y equals 0, you have plus or minus root 10 0. So we basically put the y equals 0 into the constraint equation, and then we solve for x. And then we had lambda equals 1/2. And what I did was I substituted it back into the first equation, and you got y equals x. And we substitute y equals x into the constraint. Then we solve for x, so it's plus or minus root 5. So because y equals x, you would have the 2 points root 5, and then negative root 5 comma negative root 5. Now we substitute lambda equals minus 1/2, so this is where we stopped last time. We go back and substitute in the first equation of our system. Y equals lambda equals 2x. And when we do that, we get y equals minus 1/2 times 2x, so y equals minus x. And I'm going to place y equals minus x into the constraint for y, so you would get x squared plus negative x squared equals 10. So you get plus or minus root 5. And since y equals minus x, when x is root 5, y equal minus root 5. And when x is minus root 5, y would equal root 5. And the next thing I wanted to say was, if you went back to the system of equations here, you could go and plug this y equals lambda 2x. You can plug it in for the y in there. And if you did, you would get two things. You would get lambda is plus or minus 1/2, and you would get x equals 0. And technically x equals 0 is, if you plug that into the constraint, you would get 0 plus or minus root 10. So technically speaking, that's, it's a point to consider. Now when I say point to consider, when you're trying to find the min or max of an extreme, what you do is you go ahead and plug in all the points that you found back into the original function, and whichever is the largest and whichever is the smallest, that tells you what your min or max would be. 0 and then 0 plus or minus root 10. So we plug all these points, these are the points that we got when we solve those equations. You would get 5 here, minus 5, and minus 5, and 0, and 0. So your absolute maximum value would be 5, and the absolute minimum value would be negative 5, occurring at those points. And yeah, 0 doesn't really tell you anything. It's just 0, because it's in between minus 5 and 5. Now, one thing I wanted to mention here is sometimes you will get solutions or pairs of points that are not actually solutions. So plus or minus root 10, 0, and 0 plus or minus root 10 are not solutions. The solutions that you get have to satisfy the original system of equations that we have again up right here. And plus or minus root 10 comma 0 and 0 comma plus or minus root 10, if you try those out, you're not going to get a solution. However, why is it that I would include them in here? Here's why. In general, when you're solving these systems of these systems of equations using Lagrange multipliers, lambda itself is treated often like a placeholder, and we don't actually solve for it. Often it is a lot of the time that we don't care for it. It's more like a variable that connects, provides a connection between x and y. So we really don't solve for lambda. We are supposed to, but because of time constraints, and just because it's tedious, let's say, you usually don't do that. So you basically just grab your pairs of points that you see that are solutions to the best of your knowledge, and you go ahead and plug them back into your constraint. And usually the actual solutions here to your constraint will give you your min and max. So root 5, solutions to your system of equations, like the root 5, and these four right here. These are solutions when lambda equals plus or minus 1/2. Those are solutions to the system of equations. Those actually work, but a lot of the time that lambda, what I'm speaking of, the 1/2 and negative 1/2, you won't know, and it's some work to get to it and to check that's actually an answer. It's actually a solution, excuse me. So we just go ahead and grab all the points that we would get maybe from the constraint when we try to solve the system, and then plug them back in. Okay, well, thank you for your time, and thank you for your patience with these watching these sets of videos. Have a great day.